Okay. Good afternoon, everybody. So if you remember, we were start discussing side channels, and if you remember, I said that essentially the problem of side channels is what we are trying to kind of having the inputs, having the algorithm, knowing the exact implementation, and we are basically trying to kind of find the secret information, usually the key. I started with kind of like there are three approaches. The first one, we start with obviously the simplest one, and kind of like the very first one that's kind of start being used, and that is simple analysis. Simple analysis, as the name suggests, is just we're looking at the signal and trying to find any patterns. I gave you two examples. This is actually a real example of attacking one version of RSA. Another one is more of like profiling an application. Um, and then another one is, as I said, it's usually, simple analysis is used for more sophisticated analysis, like, differential analysis I'm going to talk about. As you can see here, is kind of, you can use simple analysis to kind of know where certain things starts, right? So for example, you can know, for example, this particular thing start at this time. So you kind of can use it in order to synchronize your signal. And then the reason that simple analysis obviously doesn't work all the time because you can always hide obvious things. As soon as you know about side channels, you can start thinking how we can actually kind of like make things similar to each other. As a result, your attack no longer works. So what attackers came up with was a more sophisticated version of side channel attacks. That's called differential analysis. The idea about the differential analysis is based on this kind of fundamental assumption that if I make a decision, so first of all, like, zeros and ones create this change in power side channels or all electromagnetic. For now, let's assume that we are talking about power side channels, but essentially this applies to any other side channels, okay? So let's say I have zeros and ones, and my zeros and ones impact the power consumption. That's kind of the basic idea of side channels. Otherwise, if it doesn't impact, there is no side channel. So if there is side channel and there is zeros and ones that impacts my computation, then what I can do is that if I kind of collect signals based on two different kind of observation. One is like if I do bit one versus the other one is doing bit zero. If the signals are indeed correlated with this event of 0 and 1, if I can kind of like say that, okay, these are all the events for signal 0, these are all the events for signal 1. If I subtract these two, I should see that difference, right? And the idea is, can I actually kind of do that classification? If I can do that correctly, then there will be difference. So in other words, if I see a difference, it means that I classify it correct. Right? So that's kind of the idea of differential power analysis. So let me actually give you an example. So this is what's called, the DES, encryption key. It's very kind of similar to AES, before AES. And DES, similar to AES, has like multiple rounds. Usually it has 16 rounds instead of like 10 or 12 or 14. And each round is essentially like if you have like a key like an input like this, you divide it into right part and left part. And then in each round, what you do is that you send this right part to this thing we call S box, pretty similar to what we do with the AES. Then we XOR it with the left part, and then this would be the new right part, and then this would be the new left part. So basically the image I'm showing here is also pretty much the same thing. So this is the right part. The right part goes to this black box, which is an S box. The S box basically has two inputs. It has the right part and it has the key of that round, which we usually call it subkey. And then there's certain things happening in this S box that I'm going to describe later. But the output of this S box is then XORed with the left side. And then we have now this kind of intermediate value here. This would be the new right part. The right part becomes the left part. And it's kind of like, you keep switching this 16 times, although the last time is slightly, so this is for the last time, slightly different. and then I'm gonna get my encrypted version of the message. Okay, this is just a regular encryption, very popular before AES, still being used sometimes. So this is general idea of how this would work. Okay. So let's see how we can actually use the idea of differential power analysis in order to break this mechanism. And of course, the idea here is that we need to find these subkeys, right? So the idea is, can I, by doing some analysis on power, eventually find this? And then this is the last round. So this is actually the actual ciphertext that we are observing. And the idea is that I'm going to start from the last round and kind of work my way up back to the original round. Okay, that's kind of like what we're going to do. All right. So, so how do we do this? Okay. So the idea is that I need to make some assumption about the key. Okay. So for example, let's say I start with zeros, all zeros. Okay. And then doing some analysis that I'm going to describe and see whether that assumption was correct or not. If it was correct using DPA, then it means that my assumption, my guess about the key was right. Otherwise, I go to the next one and I go to the next one, right? So that's kind of like what we are trying to do here in order to break the system, okay? So how do we do that? We start with this very simple observation that let's, for example, assume that all these bits of right and left are all random except this last bit here, okay? This last bit, the most significant bit of this last round of DES, and we want to see whether this is 0 or 1. So basically our classification would be based on whether this is 0 or 1. And our hypothesis is basically this, that if I can categorize the signal based on whether this is 1 or 0, then I should see a differential power analysis phenomena, which if everything else is the same, but only this bit is changing, there should be some difference in the power signal that I'm seeing. Okay, that's kind of the idea. Okay, so I want to kind of make some assumption, make some observation based on this last bit. Okay, so how should I do that? So in order to find this last bit, okay, so first of all, if you kind of follow this last bit, it kind of goes here. So I need to know this value, but then I can observe this kind of like this final value here, basically. This kind of, yeah.
Can you change the color of black? The black.
Oh, you cannot see the black?
Yeah, thank you.
Sure. Let me see. Can you see this?
Yeah, I can see that better. Thank you.
All right. So let me see if there's any. Which one is better?
Purple.
Purple? Okay. So let me do purple. All right. So the idea is that if I kind of like make assumption on this, all right, I need to know what this is. And then what I will see is that basically this goes here, right? So, and I already know this. So this one I know because this is the output of the ciphertext, okay? If I somehow know this or make some guesses about this, then I can know this as well, right? So here's what I'm going to do. So I'm going to make some guesses and then find this. And then based on that, I'm going to basically, predict this. Then I'm going to have some signals and then I'm going to categorize them based on whether this is 0 or whether this is 1. And then I'm going to test whether that kind of guess was correct or not, because that kind of guess was based on this thing here. If it was correct, means that I made this guess correct. Okay. So why this guess is important? So let's actually kind of trace this back. So first of all, this is kind of like coming from this part here. This is coming from this S box here. This is coming from this part here. And again, as you see, this is basically where the key is, okay? So if I make some guess about the key, okay, I have some, let's say I start with 0, 0, 0. So this is all zeros, okay? I have some guess about the key. And another thing that I have is that I have all the bits here. Basically, I have this number as well. So everything about R16 is known because R16 just directly goes into my ciphertext. So I know R16. So I know everything here already, okay? I also know the mapping between these, so I know this part as well, okay? So all I need to guess is this key. Once I know the key, so let's say I start with all zeros. I know this part, I make a guess about this part. So now I know this part, this part, this part, all the way to here. So I know now, based on my guess on the key, I exactly know what this value is. Okay? And now that I know this value and I know this value, then I can predict this value, right? So based on all of these things, it started from, I just don't know this, right? So I start from all zeros, and then I propagate through everything, and then I eventually can say that for this particular experiment, whether this was 0 or whether this was 1, okay? So now I have for every single time that I run this, based on this assumption that, for example, key is equal to all zeros, I know whether this 1 bit is 0 or whether this 1 bit is 1, okay? So what I do next? What I do next is basically, let me see if I can add a, sorry. Keep changing this for some reason. All right, so I have my key, I had my right part, the right part kind of comes in, the key also comes in, and then there is some form of like shuffling and all these things that you don't need to care about. Then there is like the left side, and there is this 1 bit. This 1 bit comes, this key comes, XOR together, and then creates this 1 bit here, right? So I know this, I can observe. So what I do is that now I'm going to start kind of creating lots of messages. Message 1, message 2, all the way to message n, okay? So for each message, I will see this bit. I know my key, I can propagate this through, and I can see whether for this, let's call this MSB, I know that for this message 1, whether MSB was 0 or 1. 0 or 1, 0 or 1, okay? So for every single one, now I know whether that 1 bit was 0 or 1 based on the assumption that I had for key. So this is just for key equal to 0. For key equal to 1, I need to repeat the same process over and over again, okay? But let's just start with key equal to 0, and we want to check whether or not key equal to 0 was a correct guess or not, right? So I have this, and I know the answer to this question of whether this is 0 or 1. What I'm going to do now is that I'm going to categorize these based on this bit. So those that are, bits is 1, for example, this one and this one, they all go to group 1. Those that are zeros, they all go to group 0, okay? So these are actual signals. So for example, let's say my signal looks something like this. So M1 is something like this. M2 is pretty similar to this. Of course, I cannot visually see the difference between them. But what I know is that, for example, for this one, the bit is 1. For this one, the bit is 0. So I'm going to categorize this in group of 1. I'm going to categorize this in group of 0. Okay? And I'm going to repeat this for all the messages. Let's say thousands. And how many depends on like how much you want to do the average. Okay? So I'm going to have lots of signals in one group and lots of other signals in another group. Okay? So what now I need to do is I need to do the average. Okay? So I do averaging of this group. I'm going to do the averaging of this group. I'm going to get 2 new signals. Okay? Let me add another page. So I'm going to get 2 group of kind of representative signals for group 0 and group 1. And then I'm going to subtract these 2 from each other. Okay, subtract. And then I'm going to get either something like this, or I'm going to get something like this. At some point, I don't know where that point is, because that's the point that basically that 1 bit was being computed. I don't know exactly where that is. But what I know is that if I just kind of randomly classify this group to each other, what I had done was like my subkey was wrong. So I just classified these 2 groups randomly. So there is 50% of chance that, zeros is here is correct, and there is equally 50% chance that this was correct. In other words, I'm just averaging two random variables together and subtracting those two random variables from each other. So based off statistics, I shouldn't see anything. They should see a flat line because I'm just subtracting noise from noise, which should be noise, right? Versus if I actually do 100% accurate, so I actually indeed did the classification correctly based on the correct assumption about the key, then I exactly kind of amplify this exact difference between the everything else is random. Only that one tiny slice of window that that particular bit was being computed was different. So I should see some difference, okay, some form of a spike, some form of a difference between this. So if I see this, it means that my assumption about the subkey was correct, okay? Because remember, all of these things started from this assumption. So I started from this was equal to 0, and I did all of these things, and then I do the subtraction. Most of the time, I'm not going to see any difference, which means that this assumption about the key is equal to 0 was wrong. But at some point, when I actually go through all the keys, at some point, I'm going to see the difference. And that's the indication that this was a correct assumption, okay? And this way, I'm going to find the key 16, the subkey 16, okay? And that's how we're going to break basically this algorithm at this subkey level. Any questions? Make sense? Yeah.
How granular does the attacker have to be, or accurate their equipment, I guess, to measure the power? And at
Yeah.
what level, it's not gonna be from the wall, it's probably gonna be just the CPU, right?
Yes, that's a good question. So the question is about the accuracy. So if you look at the signal, I'm assuming that I have enough time granularity that I can see the kind of 1-bit calculation. Okay. If I cannot see 1-bit calculation, I can see only kind of all the bits together, then they kind of average each other out. Okay. So kind of the implicit, assumption here is that I have enough time resolution that if you have 2 XOR of bits, I can really see that, you do this first and then you do this first and so on and so forth. So time resolution. And then another thing is when I see spike, don't think that, there is going to be 5 volts difference. We're talking about millivolt, microvolt. So your kind of detection in the level of voltage. If, for example, you're doing power, if you're doing EM, it should be basically, the dB amounts, signal to noise ratio. And generally, your signal to noise ratio level should be very sensitive that you can detect this, okay? So how small it is, it's a function of the device, it's a function of your equipment, there are all those things, how fast the switching happens and all those things. So there are lots of practical issues with this, of course, that you need to consider.
And also it can't be the overall system power, because that would just muddy everything.
Oh yeah, of course. So you have to be very you should be able to only see that particular. Yeah, if for example, lots of other things going on as you're kind of XORing these 2 bits, then what you're seeing is it's a superposition of these 2. And then if this one is dominant to this one, then you don't see the difference.
But even if let's say you only measure the power at the CPU, it's gonna be doing other things in the background, right? So it's gonna mess up your.
Depends. So for example, most of these things are using some form of embedded system, for example. So it's not you have tens of other things happening at the same time. You time multiplex these things, right? Or there's a particular coprocessor or something. So you have your CPU and you have your crypto engine. And if you want to read the power, you just read the power directly from your crypto engine. So it doesn't matter what the CPU does. You're just looking at that coprocessor. So there are these tricks that you can do in order to make this more visible. But yeah, of course. I mean, always background noise and side channels The huge problem.
Oh.
Yeah.
Thank you.
All right, so that's kind of what the differential analysis is. This figure kind of like summarizing it this way. So I have some form of a setup that I can measure power. Okay, I kind of run it with multiple different plain texts, right? I observe the ciphertext based on, for example, that one bit that I see. I kind of do some computation in order to kind of make a decision about each run. So I'm going to classify some of the runs in group 0. I'm going to classify some of the runs in group 1. I'm going to do this many times. So this is just not one. As you can see, this could be like few thousands of traces. So I have few thousands of traces for one group. I have few other thousands of traces for another group. Then what I'm going to do is I'm going to compute the average. Okay. So I'm going to have just one sample that is the average of all of these. One sample that is average of all of these, and then I'm going to subtract these two. I'm going to either see this or I'm going to either see this. If I see this, it means that this assumption about the key was just a wrong assumption. As a result, these groups are just nothing but just random grouping of these different traces. There is no real difference between them, so I shouldn't see any difference. If I made a correct assumption, then boom, I'm going to see this kind of peak here because I actually did classify this correctly. Okay, that's kind of like the idea of a differential power analysis. Okay. As I said, differences is, sometimes it's really hard to know when I should do differential power analysis. And sometimes that's why we kind of combine SA with DA, as I said. So for example, you kind of know that, oh, this is the beginning of last, round of DES. So what I can do is that now I can kind of start running my differential power analysis. So, the noise complexity, all this discussion that we had, that's exactly the problems that you're going to observe in a side channel analysis case. Okay. All right, so we talked about simple analysis. We talked about differential analysis. Let's actually talk about a more modern approach, which is called template analysis. And as I said, I want to kind of, again, emphasize that you can have power, you can have EM or electromagnetic, and you can have a bunch of different things like temperature and so on. So that's why we usually, when we say simple analysis, we say, for example, simple power analysis, or simple or differential power analysis, like you probably have heard about DPA and SPA. When we say DPA or SPA, means that, in terms of power as a side channel, you can, for example, do SEA, which is simple electromagnetic analysis, or DEA, which is kind of electromagnetic differential analysis, and so on and so forth. Okay, so in principle, all of them is the same. It's just the channel, the signal that you're measuring differs. Okay, but otherwise the algorithm stays exactly the same. Okay, so now let's talk about the last one, which is the template analysis. And this is where we're going to actually kind of involve more sophisticated signal processing and, of course, machine learning to this. Because so far, this is just a pure kind of deterministic algorithms. So the idea about template analysis is that we're going to have exact copy of the device that we're going to attack. Okay, so none of these devices are unique. So for example, if you want to attack a Raspberry Pi, let's say, you can buy a Raspberry Pi for yourself, right? So, and then what that's kind of copy, the template of what you're going to attack helps you is that you can build models, you can learn the behavior of that device in some offline time. And then based on this knowledge that you have gathered, you can actually attack the system maybe more intelligently, more efficiently, in more successful, and so on and so forth. Okay. So what we're going to do is that we're going to take an exact copy of the device. Of course, there is slight physical differences between any two exact copy. That's something that we're going to discuss later. But let's assume that, instead of attacking the actual target device, I'm going to attack another similar device. So what is the difference between these two? The difference is that the similar device is the owner of that similar device is me. So I can actually know what is the key, what is the input, what is the output. I have full control over that system. So what I can do is that I can build a model that knows exactly what is the key, when is certain things happening, and all those things. So I have a controlled environment of everything, including the secret. I build a model based on that, and now that I have my model, then I'm ready to attack the device that I want to attack. Okay, so I build a model based on running lots of x and f of x, and the difference here is that I also know what the key is. Okay, because I'm the owner of the device, I can set the key to whatever I want, and then I attack my own device in order to build the model. Okay, so this is basically similar to training of any system, especially machine learning systems that we have for other things, like for image classification, for example, right? We have a bunch of a big data set of images and labels of those images. Use that to train our model, and then once we train our model, say that okay, let's actually apply to a new image that we don't know what is the label for it, right? And then that's where we're going to test the system in this security context. This is where we're going to actually do the actual attack. Okay, of course it's not always correct, which means that there is also potential for kind of misclassifying and incorrectly doing it. But if my system is accurate enough in most of the time, then I have a successful attack most of the time, right? That's what I want. So I have my training, then I kind of like take my training model and applying it to the testing model, which is the actual attack scenario. Okay. So to give you an example, this is actually one paper that we did. So for example, let's say that I want to see what is the signal. Okay, so I observe this kind of like pattern behavior, and let's say this signal is, let's say I have a code like this, that if some condition, do A, else do B. Okay, so and then let's say A and B are just like sequence of things, like I don't know, add two numbers, subtract two numbers, and so on and so forth. Okay, so let's say that I want to know whether A was executed or whether B was executed. Why would I know that? Because, for example, if I can tell you that A was executed, then you know what was the condition, whether the condition was true or not. And now, if you remember when we were talking about simple power analysis, we said that basically this is usually based on the secret. So let me actually go back. If you remember about the SPA, I had this example here, and if you remember, we had a scenario like this, that if D was equal to 1, we were doing something. If D was equal to 0, we were doing something else, right? And this D was part of my secret key, if you remember about RSA. So if I can't tell whether or not I did the if or I did the else, I basically know whether D was equal to 0 or whether D was equal to 1. So I basically know the secret. Okay, so based on this, I'm going to do this attack where essentially I'm trying to see the signal and say that whether this signal belongs to A or whether this signal belongs to B. So how do I do that? So I don't know this and I don't know the answer to this, but back to the template, I can run lots of these instances, sometimes with condition equal to 0, sometimes the condition equal to 1. I'm going to get a database of taken branches and not taken branches. Basically, taken branches means A, and not taken branches means B. Okay, so now I have a big database of this. Now what I can do is that during the attack phase, I basically compare this with all of these instances that I have. And then I use some distance metric to see the similarity. For example, here we are just using a basic cross correlation or just a Pearson correlation between these two signals. And what will happen is that, for example, I can assign scores. So for example, this one says 92%, this one is 0.79, 13, 0.16. And basically this means that it's very, very likely that this signal is coming from a taken branch. In other words, this D is equal to 1, right? And as I said, this is not guaranteed. It's not 100% correct, but most of the time it's correct. Then most of the time you know what your D is, right? As simple as that. And that's basically the idea of a template analysis. Okay. So of course there are lots of questions, right? So for example, what is the right metric? How do you train? What's the distance? How do you measure the distance? And all those things. And these are all quite good questions. They're questions that really depends on the domain. It really depends on the attack, really depends on the device. Next week, when we are actually presenting some of these papers, you will see some of these things in the paper presentations, but generally there is no specific answer to what is this, okay? You can use correlation, you can use general machine learning, you can use some distance metric, similarities, you can use all of these. Essentially, this is the comparison or classification problem that exists in many, many other instances of electrical engineering, computer, generally data analysis or data science, that I have an instance and I want to label it to some classes. How do I do that? That's the learning problem that we're facing in many other, part of the science. And then machine learning, of course, is always one of the major candidates for doing this. So what I can do, for example, in this particular scenario, is that instead of like doing correlation, I can feed this signal into some machine learning model. And then this machine learning model basically has two classes, taken or not taken. So it's going to give me a 1 or 0, right? I can train this model with this way, and then boom, it works.
For the one that you said distance, is that just like pointwise distance or?
Oh yeah, for example, if I do correlation, I just measure the correlation between, these are two vectors, right? So you can measure the correlation between two vectors. You can also make this a 2D and then measure the distance between a 2D image, right? So there are lots of similarity distance metrics. Okay. Let me give you another example. This is called one and done. This is an attack on RSA algorithm. So the idea of the attack is this, okay? So there's this, again, an RSA blinded Montgomery constant time, multiplication. And the way it works is, it basically works on windows of data, okay? So it takes 4 bits or 2 bit or 4 bit or something like that, and then either do a square multiply or just do the multiply, okay? And then sometimes it's just doing some things such as do the pre-computation to kind of not doing the multiply and so on and so forth. So what these guys found was, essentially, if you are looking at, if you're looking at this signal, there will be kind of like lots of things going on, but there is this very kind of prominent signature that's kind of like the signal is kind of looking like this, then jumps up and then doing something, and then there will be a window. Well, what they found is that, there is a time between here and here, and this is basically where this multiply happens, okay? So this like tiny bit of signal is when this particular kind of multiplication is happening. And again, the reason that the way that they found this is using a template. They basically, as I said, you have control over the entire system. You can exactly time everything, and they made this observation that, oh, I can find this, and I have always, there's kind of an offset to this, which is always constant. And this part is the part that's kind of this kind of secret dependent activity multiplication is happening. So you chunk this signal, this part out of the signal. And then what you would do is that you will see that, for example, there are multiple different versions of this instance that you can look at. For example, if you have a device A or device B, and then you have 0 and 1 version of each one. So if your secret is 0 versus if your secret is 1, you will see that there's actually a very clear difference between them, and they actually match pretty well together. So you will see that, for example, for both device A and device B, the 0, the secret is equal to 0. It kind of like looks like this, versus the secret equal to 1 looks like the black signal here. So, and then you can clearly see the difference between the black one from the red one, right? And then it's the nice thing is that even for one device to another device, although there's kind of tiny bit of difference, but they're kind of matched together, versus the black ones obviously also kind of matched together. So that across devices, there's tiny bit of variation, but that variation stays kind of constant in some sense, versus the variation between 0 and 1 is kind of very, very significant. Okay, so basically all you need to do is that you can actually like look at this signal here, and again, using some form of distance metric. So for example, in this particular case, you probably just can do some form of a simple correlation. And you can see whether your signal looks more like the black one or whether it looks like more of the red one. If it's the black one, then you have your answer. Your secret was 1. If it looks more like the red one, then your secret was equal to 0. Okay, and then as I said, these guys repeated for various different devices, and they saw that almost all of them follow basically very similar pattern. There's tiny bit of differences, as you can see here, as I said. So for example, like this one is kind of tiny bit of shift from here to here, but this shift is tiny enough compared to the difference between the red one and the black one, right? So it's kind of inter-device variation versus 0-1 variation. Yeah.
So is this signal like the zoomed in on that spike down?
Yes. So this part is this part.
Oh, okay, got it.
Yeah. And then the way that they found this part was they kind of really spent time on this algorithm, and they found that, oh, okay, this is the part that's actually belong to this, because everything else is not secret dependent. So I don't care what's going on before or after. This is the part that actually takes, the message and the secret key, and then actually does secret dependent activities. So if I can tell the difference between 0 and 1 for each bit, then I know the secret, and then I can break this crypto method. And then they have pictures of real systems, like a mobile device and all those things. So generally, to summarize, by systematically analyzing a given code and having a sample of the device that you have, you might be able to extract valuable information from the attacker's perspective. And then you can use various different tricks, combination of just code analysis, running multiple experiments, and then of course usage of signal processing and machine learning in order to break that system. Okay, so that's kind of like the idea of the template attacks. The various different scenarios for this. I just gave you one example of this particular algorithm. Like all these timings and everything was just very, very specific to this algorithm. It doesn't really translate to anything else. But the reason I wanted to show you to this is that it's possible to do this even for secret systems. So this is supposed to be actually kind of resistance to side channels, but these guys show that it's not. Okay. All right, so what time is it? Oh, okay. So there are different options for side channel analysis. Most of the things that I show you so far are time domain signals. Like you sample your signals over time, and then you do your analysis, right? So basically everything becomes like a vector or time series data. That's kind of like you have samples, and samples are timestamped with kind of like your clock or whatever. And this is all of your analysis, but you can easily also do frequency level analysis, right? So you can take FFT of this time domain signal and do your analysis on that. There are many works that does that too. And again, as I said, this is basically nothing new in terms of analysis. This is similar to many other systems that we have. You can also kind of transform this into some intermediate mapping, right? So either not timing, not frequency could be some a latent version of something that you can use. We usually do lots of pre-processing when you are doing this, including taking out the portion that we really need to look at, or to kind of do lots of averaging in order to reduce the noise. For example, if you have background activity, you want to kind of average it over so that background activity is kind of average itself out. So there are lots of kind of tricks, signal processing tricks that you want to do. So if any of you is doing any research in relevant areas, you will see these kind of tricks that people doing, dimensionality reduction, normalization, etc. These are all standard methods. As I said, like noise removal, synchronization, alignments, this is a big part of any sort of physical side channel attacks, because you need to know exactly where things happening. If you don't know, then your system won't work. So what are the main challenges? The main challenge is the interference, because the signal that you're measuring is not just coming from the device or coming from that component. Many other things can also kind of have impact on your signal. For power, it's slightly better. For example, for something like EM, because EM is just any other radio frequency activities that also have an impact on your signal. As a result, EM is basically riddled with interference. The second problem is device variation. So, for example, for template analysis, I basically implicitly assume that if I have a replica of this device that I want to attack, the behavior of this device and this device are exactly the same, right? So if I see something here, I will see the same thing there. But probably those of you who are working on hardware design and so, you know that there is this process variation, this device variation, that even same replica of the same device does not necessarily do the same thing. So we need to kind of also kind of predict that from this model to this model, how much things are changing, right? So again, if you're know about machine learning, there's things like transfer learning that we use, that if we are training a model in one domain and we're going to go to another domain that is kind of similar but slightly different, you need to kind of update your model, right? You usually update the later stages of your model in order to kind of transfer it to another model. Or maybe you can also kind of add some you can mimic the behavior of device variation in your model, so that your model is actually robust to those kind of variations and noises. So there are tricks that you can use, and again, this is the part that things like machine learning and AI help significantly to improve this this area of side channels attacks. Not only there will be interference and device variations, there will also be temporal or runtime variations. That, for example, for a very short period of time, there might be some other interferences, like somebody come into the room with very strong radio frequency source of interferences. So it's not like I always see this interference. Sometimes I might see this interference, sometimes I might not see this interference. So this further complicates things and makes it very hard for the adversary to run this. And of course, the last thing is the sampling rate, or general signal to noise ratio, and SNR, which you want to achieve as much as possible signal from the device. If you can do that, then you can have a more successful attack. Yeah, so let me see. Okay, let's have a quick break here. I'll come back and talk about the rest. All right, so there are different types of side channels, obviously, as I said. The main difference between them is the channel that they use. We kind of talk about, electromagnetic power, acoustic. There are also newer side channels, which I'm gonna briefly discuss some of them. Another major difference between different types of side channels is kind of the thread model, right? So some of these side channels needs to be kind of measured very closely. Some of them are actually can be measured from some distance. And you might need like a very high end and very sophisticated equipment for measuring this. You might need lots of like higher sampling rate and all those things, or the things that you might extract could be very tiny or could be very big. So there are various different things that you need to consider when you're talking about side channels. The research in this domain these days is also kind of like continuing those traditional ones, but also lots of work has been done and kind of discovering new side channels. Okay, various different things, such as, oh, if you actually kind of like change the refresh rate of your cell phone, that's actually based on the content. So someone can basically, by just looking at the refresh rate, can see what's happening on your device. There's the one that's kind of very interesting, is this one called streaming side channels. So this one is basically based on this fact that many of these SoCs that we have these days are what we call mixed signal chips, okay? Which means that we usually have some like analog radios as well as some digital logic and some memory, okay? So you have a digital part and an analog part sits next onto a same physical chip, okay? So what could happen is the switching activity of this digital part essentially also impacts this analog part. And if this analog part is actually a radio, what you will see is that the signal that this radio creates is impacted by this digital switching, okay? So for example, look at this signal here. So this is what we call a waterfall plot or a spectrogram. So here I'm showing the frequency. So this is frequency and this is time, okay? And the colors here is the strength of the signal. So the more yellow, the stronger the signal is. The more red, the weaker the signal is, okay? So when the radio is off, what you will see, and this is like 2.4 gigahertz, which if you're familiar is the frequency range for Wi-Fi or BLE. This is a Wi-Fi chip here, okay? So what they found is that if they receive this Wi-Fi signal much away from the device, like 10 or 20 meters away from the device, what they found is, like, when the radio is off, of course you don't get any signal. When the radio is on, then you get some signal. Obviously, this is a Wi-Fi signal, of course you should receive it. But the interesting thing is, if you turn your AES on the digital side, so if you actually start doing some computation on the digital side, what will happen is that you're going to see some very specific patterns in the RF signal in the frequency around 2.4 gigahertz. And this could reveal what you're actually doing here. And this part here is a classic like DPA or SBA or whatever you were doing before. So there's nothing new here. The new thing here is that this is modulated on top of the Wi-Fi signal. So now all you need is, if you are able to receive the Wi-Fi signal of this device, you can actually attack this device. Yeah, you had a question, Andrew?
It's also when the radio is transmitting, or else it wouldn't have that sort of behavior, right?
Yeah, so the radio is on, so it means that it's sending things on the background. So because these two things are independent from each other, obviously. So you are also kind of like, for example, you want to send a message, right? You want to send a message using your Wi-Fi signals. In order to send a message, you usually encrypt it and send it, right? You never send a clear text message. So what you would do is that you encrypt it, so you need your AES, and then you send it to the radio, and the radio kind of propagates it through the air. But what would happen is that, interestingly, for some of these devices that's kind of the switching, the power consumption can leak into the radio, then this could be actually observed from many distance, like many meters away. So all those things that I said that, for power, you need to be very close, you need to have very good SNR and all those things. With something like this, a streaming channel is basically means that it's significantly more amplified. because now the attacker can just basically sit like 100 meters away. As long as they can observe your Wi-Fi signals, then they can attack your system, right? So that's actually kind of very interesting in terms of like, you know, observations. And then there are a whole bunch of these things. As I said, there are like lots of these attacks like this. I think one of the papers next week is going to be about kind of similar thing like this. People have found that that you're kind of like, you know, the message that you're sending and receiving to your AirPods, you know, Bluetooth, you know, speakers or headphones. This is actually kind of like follow the same thing. So that's, for example, if you send a message to the wireless to the Bluetooth headphones, the message that you're sending is kind of has this physical side channels attribute to it, so somebody can actually break into it and find that message by just observing this Bluetooth signal. Yeah. There are many various examples. As I said, you're going to see some of it. There's another interesting one that people have found that if you have a CPU and you have an FPGA, so this is your CPU, this is an FPGA, they're not connected to each other, but they share the same power. People have shown that, one of you will see it next week, that essentially the power consumption of this CPU will impact the power consumption of this FPGA. So if I actually can somehow measure the power consumption of this, I know what's going on here. And consider this, for example, in a cloud environment that you have your CPU and FPGA. You can control your FPGA, you cannot control the CPU, but basically all you need to do is just measuring your own power, and based on measuring your own power, you know what's going on the CPU side. Okay. So let's talk a little bit about the defense as well. There's also lots and lots of work on the defense side of physical side channels. One thing I want to talk about physical side channels is that defense is usually much harder than digital ones, although we didn't discuss the digital ones. But the reason that, you know, for physical side channels, the defense is much harder is because they are rooting in physical characteristics of device and they cannot go away. You cannot change the system to not transmit or leak or those kind of things. So you cannot really change or eliminate the source of side channels, versus in many of the digital ones, you can actually remove it by designing your system better. So what do we do in order to defend against side channels? Let's see if you guys have some ideas. What do you think we should do? Suggestions. Give us your intuitions. Yeah.
We could study maybe should we have like a deep understanding of the physical system.
Mm-hmm.
How it operates and what kind of information you can put on the world. Like if you're working with anything that deals with higher frequencies, have a little bit of understanding of RF.
So now let's say I understand it. What should I do to remove it? That's my question.
Like you know, with what we did with the pacemakers is put in physical filters. Things that can directly target those particular sources.
Yeah. So kind of some form of shielding, physical shielding, that the signal doesn't go out or go in could help us, right? So I think for your paper was things were injected inside the device and they were putting a shield. But same idea can happen here, that things are going out, you put a shield that doesn't go out, right? So shielding definitely helps. Great. Anything else?
Should be input independent. They should not change based on.
Yeah, so if it's input dependent, so if, in other words, if it's oblivious to what you're doing, then it doesn't matter if you measure it or not, right? So if I, like, for example, the example that I gave was I had this condition and then it was like A and then else B, right? And the whole problem was I have like my activity was based on this condition, okay? But let's, for example, consider this. Then it doesn't matter, right? Because in both cases, I'm going to observe the exact same thing. So even if I can observe it, no new information is given to me, right? So you might wonder, okay, how do I do this? And then we're going to talk about this oblivious programming. You can add dummy activities and all those things. But in other words, if I either don't have this condition or if I have a condition but do exact same thing in both scenarios, then it doesn't even matter whether the attacker can observe this or not. Yeah.
Let the attacker get a hold of the physical device, because the physical side channel, so a lot of the attacks we talked about earlier. You don't have to scope to the chip essentially.
Mhm.
So you don't want to have your attacker be able to trouble the device.
Yeah, so physical security, right? So make sure that they're not getting close or doesn't get closer than it should be and all those things, right? For example, if I have my device locked up in this room and then these doors are locked, and if I know that, for example, the signals doesn't really go outside this room, then I'm safe, right? So I can make sure that the system is working. And yeah, that's also like a physical defenses is a great one. Of course, it may not work in all scenarios, but in many scenarios, that's a great defense. Anything else?
For the previous example, where you gave that, like you measure frequencies,
Mhm.
being like broadcast by a chip, would it be possible to perhaps like broadcast noise to like model the frequency that's being measured?
So you randomize, right? So you kind of confuse the attacker. That you also sometimes, so for example, you do this, maybe you sometimes also send B, sometimes do A. If the information that is received by the adversary is the random process of various different things, including what you do and including things that you don't do, then again, there won't be any information, right? So you have to remove the actual mutual information. You have to increase the entropy. If you increase the entropy, the adversary won't understand it. Anything else? Okay, I think we talked about most of the things. So the first thing, I think, as you said, making things oblivious or constant time. This is mostly at the software or compiler level, right? So your algorithm has to be oblivious to the secret. Of course, the challenge for this is that we need to have a model of the actual physical signals, so that if you're actually doing things, we have to know whether, for example, if I do this activity versus that activity, are they different or not? But there are lots of works, especially at the software and compiler level, that tries to make the program either what we call constant time or oblivious to these type of attacks. The other thing is that, of course, we make the leakage go away. For example, if you have what's called a Faraday cage, if you have like a metal layer around your device, then there won't be any kind of electromagnetic signals going out. If, for example, if someone's trying to kind of measure a particular pin in your device, then if you kind of like protect all your pins and doesn't let anyone in to kind of like look into you don't expose your pins, then your system, of course, is secure against those. And then for others, for example, if they're listening or they're measuring temperature, if you do some form of isolation in general, then your system will be secure. The fourth one is adding randomness. In other words, you want to decorrelate the signal from the actual physical activity, right? Or the actual secret that you're doing. If I just basically do random things whenever I have the signal, then the adversary cannot make that connection. Remember, for example, for DPA, we talked about this fact that whether I'm doing 0 or 1, at some point impact my signal. So if it doesn't, then doesn't matter what I do, there won't be any information for me to extract, right? So adding randomness will help me with that. Limiting the physical access as your classmate suggests. If I put my computers in some safe place, then I'm good. If you remember, I said that one of the big challenge of this is that the trend that we have with IoT devices is kind of opposite of this, right? We are moving toward more devices and more devices in more public places. That's why actually this problem of like side channels attacks is being exacerbated, right? that you want to have these devices in secret places and so on. But for example, your phone or your watch and your kind of like, various different things that you have, you carry it with you, you go to the, I don't know, bus, you go to airport, you go to these places, and this just gives an opportunity for a hacker to access those. So if you stay at home, then of course there will be less and less challenges here. All right, so that's kind of it with the defenses. If you're interested, there are a whole bunch of works in any of these areas. I definitely recommend you to take a look at them. For example, this oblivious programming and constant line programming is very interesting area of research. Let me finish the discussion of side channels with covert channels. If you remember, I told you that there are kind of two motivations for side channels attacks and side channels in general. One is we use side channels in order to kind of extract something from the device, extract some secret, or I can alternatively use side channels to communicate secretly with some outside device, okay? So why do we need that? The need for this is, as I said before, is because of air-gapped computers, that many of these computers are controlling their input and output such that you cannot communicate things that are not authorized to, right? But with this covert channel, then you can do that. So how do we do that? The main idea in all of these covert channels is this, that I'm going to modulate a message using a physical activity, okay? So like that, like what? So let's say, for example, there are papers that shows that, for example, if I have a hard drive that has like this LED that's kind of blinking, okay? If I want to send 0, I blink twice. If I want to send 1, I blink maybe 3 times, okay? And then if somebody has a camera, like, I don't know, on the other side of the street that's kind of sees my LED blinking, they can basically see whether I'm sending 0 or 1, okay? And I can send an infinite size message with this blinking approach, right? So basically I take 1 bit, I either like do blinking twice or I blink 3 times, and then I wait for a little bit, and then I do repeat it for the next bit, for next bit, and next bit, and next bit. I can send arbitrary size messages with this approach. And all the attacker needs to do is basically having a camera somewhere else. No other method of communication is needed here. Of course, it has its own limitations, such as, if there is there's no line of sight between the attacker and receiver, so this approach won't work. But there are many different instances of this. So this is just an example. Generally, any physical activity could be used for a covert channel, okay? Measuring temperature, measuring sound, measuring power, changing the refresh rate of your phone. There are a whole bunch of different works that people have shown that there is covert channel for it. Yeah.
So the difference between a covert channel and a side channel is just modulating a signal for it?
Yeah, so the covert channel is using a side channel for communication, in other words. So the covert channel part is the act of sending it, is the communicating it to the outside world. So they are using side channels, but for communication purposes. So here the adversary has access to the secret inside. They don't have access to break it out to the open world. So they use this trick in order to do that. So for covert channel, you need 2 players. Both of them should be the attackers. One inside the system that doesn't have control to the IOs, and then using this physical phenomenon to send it out. Yeah.
Is there like some sort of speed limitation on how much data we can send?
Yes, that's actually a great idea. And let me see. Yes. So the bit rate is kind of like one of the big challenges here. How fast can I send this information? And that depends on what you want to send out. So for example, if you want to send out a password, which is like, I don't know, 12 characters or something, you probably want to send out like what? Like 8 times 8, 64 bits, something like that, right? So if every character is 8-bit and your password is 8-bit, 8 character long, we're talking about sending 64 various different bits. So, and then even if each one takes like 30 seconds, you can do it in half an hour or so. So it's not a bad You can do it if you have, but of course, if you want to send like the entire data, like terabytes of data, then you need to find something that's very, very fast, so you can send things out quickly as possible. And again, in the literature, there are a whole bunch of various different physical activities, each one different bit rate. Some of them very fast, some of them very slow. But at the end of the day, it really depends on the thread model. So going back, sorry. In order to construct this covert channel, I basically needs some basic blocks. Of course, I need a transmitter and receiver. As I said, both of these controlled by the adversary. The reason that the adversary wants to send something in the first place is that they cannot use regular channels. If they could use regular channels, they would use regular channels. The idea here is that the attackers is kind of somehow penetrate into my system, but they cannot really send anything, okay? Then they need to agree on some form of a modulation protocol, which means that, like, the could be as basic as on-off keying, which is like if I turn the key on versus I, turn the key off, right? And then of course they need to synchronize to each other because they need to figure out when is the right time to send something, how much should I wait, when I should send another one, and so on and so forth. Those of you who are familiar with communication channels, many of these things are actually exactly the same in communication channels. So any two, regular communication channels also need to come up with a modulation scheme and a synchronization scheme. The only difference between covert and regular is covert is using some physical phenomena, so it's much harder to actually use synchronization and all those things. For example, for synchronization in regular systems, you have like very synchronized clocks, but so that they can have like same understanding of the time. But in covert channels, you don't have that. So you have to kind of come up with like your own creative methods to do this. But in general, lots of these parts sharing with standard communication protocol. So if you have taken any communication course, you probably are familiar with many of these things. So what does matter the most? Like 5 different things. The stealthiness, which means that can anybody observe my communication or not? Because, for example, if the blinking is something that someone can realize that you're blinking on purpose, they can basically do something about it, right? So you want to also be sneaky and stealthy about the communication. The distance is another important factor. For example, for something like LED light, you probably can see it from like far, far away, but there is a limit for it as well. If you use other channels or other physical properties, this might be less or it might be more. The bit rate, we already discussed this. Also important is bit error rate, which means that I can send things, but how accurate that measurement is this bit error rate, which we usually use BER. So how do we reduce the bit error rate? By better synchronization, changing the bit rate, making things better synchronized and all those things. And of course, the equipment that I need for receiving the signal is important. If the equipment needs to be very sophisticated equipment versus like a simple equipment, then that changes the dynamic of your covert channel. All right. So how do we defend against covert channels? Essentially, whatever you do for your side channel is kind of applicable to covert channels. The only thing is the covert channel one, they specifically use a physical property, versus the side channel one was more of an unintentional one. So usually it's hard to eliminate covert, much more difficult thing to do to eliminate a covert channel versus eliminating the side channel, because the covert channel, the attacker actively trying to kind of use a physical phenomenon to send something. And then the last thing I want to talk about before finishing the discussion on side channel is actually, this is what I do mostly for my research as well. And that's the idea of side channels for useful purposes, okay? So far what I said is side channels is just nuisance that like creates lots of security issues for us, because essentially whatever secret that I have, this secret is kind of correlated with the signals that that is being sent out unintentionally, of course. And the adversary can observe this and then kind of find the secret, right? So there's just correlation unintentionally created between secrets in your program, the signal created, and the signal that adversary can measure, right? But you can also think about this the other way around, that if there is this correlation between information in your system, like generally data in your system and the signal, maybe I can use the signal to kind of verify this data. Okay, so this is what we call, side channels for useful purposes. The idea is, for example, let's say I see the signal, okay, and what I can tell is that if I used to see this, but then all of a sudden I see something very, very different, that's an indication that this device is not performing normally. There's something going on with this device, right? So the reason it could be, for example, there is an attack happening to this device, somebody changed something, some fault happened, things like that, right? So basically I do side channel monitoring not for the purpose of understanding what the secret data is, but basically for monitoring the behavior of the system to ensure that this device is doing what it's supposed to do, okay? So I can use it for profiling, I can use it for malware detection, for anomaly detection, I can use it for authentication, and you can use it for many, many different things. Essentially, this is kind of like the free sources of data for me to measure it externally from the device and be able to say that what this device is doing. And if I'm the trusted party here, I'm the good guy here, then I can use this for something useful, right? I can use it to understand the problems with the system. So let's, for example, look into this example here. So this is a device, okay? And again, I'm showing the waterfall plot. So this time frequency is in x-axis, time is in t-axis, kind of like start from the top, goes down. And this is a medical device actually. And it has this pattern. For now, you don't need to care about why you see this pattern, but this pattern is based on the application that we're running in this device, okay? Like clear lines here, some kind of things going on here, and then some lines here, and so on. So, okay. The interesting thing is the difference between the pattern that we are seeing here and the pattern that we are seeing here. As you can see, like there's this tiny bit here that you see that here is kind of different than here. And that's the indication that for this window of time, this device is doing something different. Something that you haven't seen before. And this is an indication that probably this device is being attacked or something, right? So for example, in this particular figure and experiment, what we did was we did some form of a buffer overflow attack on this device. I'm gonna later in the course explain what is a buffer overflow. Some of you probably know. But here what we did was we did a buffer overflow, and we showed that by just looking at this side channel signals, I can detect the difference and say that, oh, the buffer overflow is happening at this time of running this application. Okay, so side channels could be actually used for useful purposes as well. It's not just completely negative thing. Yeah.
How would you know, like, as the good guy, that that is an attack happening?
Well, the good question. So it's similar template analysis. So I'm going to do lots of running code and lots of profiling. I now have a good understanding of what is the correct or ground truth. What is the correct things what is the right behavior of this device? And then basically at that point becomes an anomaly detection, which means that I know what it should happen. I don't know what it could happen. Anything other than this is a potential threat. All right, so key takeaways from physical side channels. So physical side channels, of course, is a very, very critical vulnerabilities. The problem that we are seeing these days is that these attacks become even more common. The reason for it is that we are seeing more devices being used, more common places, more secure data. So the problem of side channels is actually getting worse. There are a whole bunch of different, side channels. There are different ways of attacking the devices, but also there are different ways of defending against these side channels. so it's kind of like a cat and mouse game between the attackers and defenders, but it's something that you always need to be worried about when you're building a system like this. Okay. We're gonna see lots of presented, like 3 different example of side channels hopefully next week. So you're gonna learn a little bit more about side channels as well. All right. Okay. Any final questions about side channels? Great. So let me quickly. All right. So the next module that we want to talk about is kind of going one step higher and talking about wireless security as kind of like, you know, to kind of completing the story of our kind of starting from the sensor, then faults, then side channels, and then finally, when this device is trying to communicate with another device, what sort of problems are going to have for this communication. This together basically creates this kind of interaction module of our IoT device. Later on, then we're going to mainly after this, we're going to mainly focus within the device. So problems that within the device we might have. So kind of ends the discussion, like half of the class going to be covered after this. So there are 2 kind of like main problems that we're looking at when we're talking about wireless security. The first one is kind of like the problem of communication, of course. And then the second is some form of authentication and authorization. And what are the problems we're going to have there and what we can do. In communication, similar to many other instances of security, the problem is confidentiality, integrity, and availability. And of course, there's also privacy issues with communication, because communication, when we talk about like wireless, means that everybody else can observe things, right? It's no longer a local thing. Everybody else can see our communication or our activities. So they can actually extract something about our behavior and our activities as well. And that's important because it's not just realizing what we do exactly, but also more of like our behaviors or patterns and so on and so forth. So a big portion of security issue related to wireless systems is about privacy aspects. Okay. For communication, of course, there are a whole bunch of works that has been done on confidentiality. This is basically trying to answer this basic question of how do I send a message from A to B, right? Securely without anybody else listening to it. And then this is heavily based on things that we discussed in the first 2 weeks, and that was cryptography primitives. And if you remember, I told you that there are primitives such as encryption, decryption, authentications, codes and hashing and all those things. But then based on those primitives, then we're going to build protocols, okay? So there are a whole bunch of different protocol network protocols such as TLS, TCP, DNS, key management. These are all using various form of cryptography, some different primitives, coupled with some different algorithms, in order to make sure that, sending a message to another device is secure. Nobody can listen to it. If they listen, nobody can understand what's happening. Making sure that, the source and the destination can kind of basically authenticate themselves and all those things. We're not going to talk about this because this is kind of like a full-on network class that you probably have taken or will take. If you're interested in kind of learning about these network protocols, I definitely recommend you to kind of take more courses in this domain. But just know that these things exist, but we're not really going to go through them. And then there are a whole bunch of attacks in this domain. There are attacks that because of the bugs in the protocols, because of the implementations, and because of the hardware, that is actually the hardware itself has problems, and the attacks are basically kind of propagated through. There's, of course, lots of side channel attacks in network as well, because even though your system kind of like your messages are encrypted, still side channel attacks applies to the network. And then, of course, there are lots of faults that you can, for example, flip bits and change bits and all those things. Again, those things actually do happen on networks and on the communication. So, as I said, this is kind of like a course for itself. I'm not going to talk more about this. But if you're interested, definitely, take a course, consider taking a course in this domain. There's another very relevant problem to confidentiality, and that is integrity. That is not only we are interested to, for example, confirm that the message that we send is nobody can listen to it, but also want to make sure that the message is the same message that the transmitter intended to transmit, right? And again, this here is mainly dominated by cryptography methods, particularly MAX. And then basically here we are kind of like have two main things that we need to protect. We usually call it data at rest, which means that when the data is stored, it needs to be protected in terms of confidentiality and integrity. But also we need to protect data in communication, that when we are sending it, we need to make sure that the data, again, confidentiality and integrity is protected. There's this third one called data in computation, which most of these cryptography method really doesn't do anything about them. But the interesting thing is that there's a lot of work that kind of like work on data in computation, like, securing the integrity and confidentiality of data during computation as well. Again, this is not something that we're going to talk about, but just know that it exists. Here, the common attacks are man in the middle that you probably have heard a lot. And then the replay attacks, which means that, the attacker tries to kind of substitute this message with some old message or take it out and not sending it and all those things. So availability, integrity is the main two things that's being covered in this area. And again, it's one of those things that we're not going to talk about in this class. Then there's also availability issues. In availability issue, there's like one big area that's many people work on, and that is kind of jamming and masking, which means that can I, for example, prove like if I have device A and device B and they're kind of communicating to each other, can I somehow force the system to not receive the messages? Basically just block everything. So having this giant wall between them such that they don't can receive each other's messages. And this is particular to attack availability, which means that you still can't send and receive messages in confidentiality and integrity modes, but I'm just trying to just go after the communication itself, right? So I want to kind of eliminate the possibility of communicating with anyone else. And this is like useful for many instances, such as militaries, wars, and stuff like that. And then the masking is pretty much similar thing, as in like, not selectively letting things go. And this is also a very, very common thing. And again, there are a whole bunch of works in this jamming and masking. And again, it's something that we're not going to talk about. On the availability side, we kind of talk about covert channels a little bit, right? And covert channel is kind of, you can think about like some form of availability in a negative mode, right? So make things available that it shouldn't have. So we kind of talked about this already in this lecture. And one thing I wanted to mention is that reliability is also kind of goes hand in hand with availability and jamming and masking. Many systems are not necessarily targeting protection against adversary, but they're targeting a system that is reliable. For example, if environment changes, temperature changes, operation changes, you can still successfully send a message from A to B. And these are all about reliability. But once you make your system more reliable, most of the cases you're making your system more secure against availability attack as well. But these are not exactly the same thing. Okay, just remember that. And then there is problem of privacy. This is one of the things that we're going to discuss. We're going to actually discuss it more next week. And this is not directly the classic CIA. Here, the idea is that I cannot really understand the message or the main components that we are trying to protect, but I can extract some metadata, some extra information about the activity that's going on, whether this is a message or usage or things like that, in order to kind of like break some other assumptions. So for example, things such as smart home activity, app fingerprinting, device recognition, these are examples of where privacy could be violated. And we want to talk about this next week, okay? So this is the problem of communication. Most of the communication we're really not going to talk about in this class, just FYI. What we do going to talk about more is authentication and authorization problems in IoT devices, okay? So what is the authentication authorization? Basically, this is the problem of someone wants to kind of show themselves their true identity. They want to show that they are the thing that you think they are, right? So for example, if I want to send some message to B, the first thing I need to know is that whether this person I'm sending the message to is really B, or is it someone else that pretends to be B, right? Or whether this message that I'm receiving, this is more important actually, if it says it's coming from B, how do I know it's really coming from B? It's not something that pretends to be B, right? We actually talk about this in the other context when we were talking about sensors, right? So Taylor Swift example of, oh, Taylor Swift send you a message and say, I'm Taylor Swift, give me some money. How can you even authenticate that this is Taylor Swift and this is not some random guy, right? So this is the problem of authentication. And then the other problem is authorization. And that is that if someone wants to do something, how do you actually kind of give them the ability to do so, right? So for example, back in the first lecture of the class, we said that, for example, we want to open a file and we suggest that maybe we can use some form of a password checking to make sure that only people who are authorized to do that, they can do it, okay? So we don't know who they are, but we have a mechanism that whoever has the password are authorized to do something else, something that we are planning for. So the authorization problem is that how can I achieve certain level of privileges following some specific formats? And of course, password and password sharing is a dominant solution here, but there is a whole bunch of other solutions that's going on, okay? And again, authentication and authorization mainly based on cryptography, and that's another use case of cryptography. But there's also a whole bunch of other non-cryptography methods that can be used for authentication and authorization that we're going to actually talk about next week. And then again, authorization and authentication is also subject to a whole bunch of attacks and bugs. Okay, so side channels applies here. Bugs and implementation errors also applies here. Okay. Then there will be physical attributes. Actually, I think this might be a good place to, let me just give you kind of like last slides and then I'm gonna let you go. What we can do instead of basically using cryptography protocols, we can use physical attributes to do authentication or authorization. So like things like biometrics, right? Location, attributes to the voice. And this is an interesting area because it's kind of intersection of sensing and all those things that we discussed so far and wireless systems. And then all these sensor spoofing and all those things that we talk about is actually translate here. So we're going to talk about these things next week a lot. Okay. All right. So let's pause here. Next week, we're going to start talking about these things one by one. Okay.